Welcome to the Deep Dive. We're the show that takes your sources, digs through them, and, well, gives you the core knowledge you need to be truly informed. And today, we're diving into something that's, frankly, everywhere. Plastic.
Absolutely everywhere.
Think about it. The cup in your hand, maybe the phone you use, your keyboard. It's just ubiquitous. But we all know this convenience comes at a cost, a really steep environmental one.
Yeah, we're talking overflowing landfills, oceans full of debris, and these tiny microplastics getting into, well, everything. Our food chain, for starters.
And it hits the wallet, too, right? Globally, this plastic mess is costing something like, what, $80 to $100 billion a year in economic losses?
That's the ballpark figure, yeah. And the core issue with conventional plastics, the petroleum-based kind, is they just hang around for hundreds of years.
Right, they don't disappear.
They just break down into smaller bits. Microplastics, nanoparticles, contaminating ecosystems, ending up inside us. And the projections are pretty dire. Without major changes, we could see about 1.3 billion metric tons of this stuff mismanaged, ending up in the environment by 2040.
Okay, so clearly we need solutions. Urgently. And that's when you hear all these buzzwords popping up.
Right. Bio-based, biodegradable, compostable plastics.
They sound promising, like a greener way forward. But are we all on the same page? Do we actually know what these terms mean? Because I suspect many don't.
That's exactly what we're tackling today. That's the mission for this deep dive. We're aiming to cut through all that confusion, define these terms really clearly.
Explore the science behind them too, right?
Absolutely. Look at how they're used in the real world, what their limits are, and maybe uncover some genuinely groundbreaking new materials that could really shift things.
Okay, sounds good. Get ready for some insights that might just change how you think about plastic every day. Let's dive in. So before we get to the alternatives, let's just really nail down the scale of this conventional plastic problem. How bad is it, really?
The numbers are, well, they're staggering. Global production hit 413.8 million metric tons by 2023.
400 million tons.
And here's the kicker. Over 90% of that is still made from fossil fuels.
Still, after all this time.
Yeah, and packaging. That's the biggest chunk. It's expected to be around 30% of all plastic use for the next 40 years.
Wow. And beyond just the sheer amount, what about the sort of hidden impacts, environmentally, health-wise?
Well, a big part is just inefficient waste management. Tons of it just leaking into the environment. But also, as these plastics age, they leach chemicals. Things like phthalates, these plasticizers.
Right, of those.
They've been linked to some pretty serious human health issues. Lower semen quality, neurodevelopmental problems in kids, childhood asthma, the list goes on.
That's a huge hidden cost, affecting our actual health.
And it starts right at the beginning. The production process itself is a major source of greenhouse gases. Over half the emissions across a plastic's entire life cycle.
And burning it.
Yeah.
Incineration, that makes it worse.
Even higher emissions, typically. It's a common disposal method, but yeah, it has its own significant footprint.
Okay, so what about recycling? We put stuff in the blue bin, we feel good. Is that working?
Well, that brings up an important point. You might hear figures like 30% of conventional plastics being recycled.
Yes, it's okay-ish.
But other data, maybe more realistic data, suggests it's actually less than 9%. Really recycled, turned into something new.
Oh, less than 9%.
Yeah. So some call it a recycling illusion. The perception doesn't quite match the reality.
Okay, that really drives home why we need alternatives. Which brings us back to those confusing terms.
Yeah.
Bio-based, biodegradable, compostable. They get used interchangeably, but they're definitely not the same thing.
Exactly. And getting these definitions right is crucial for companies making claims and for, all of us trying to make informed choices.
So let's break them down. Start with biodegradable. What does that actually mean?
Okay, so biodegradable plastics. By definition, these are plastics that can be broken down by natural microorganisms. Think algae, bacteria, fungi.
Into natural stuff.
Yeah, into things like water, carbon dioxide, biomass, natural components.
Sounds great. So I hear biodegradable, I think, poof, it vanishes. Is that right? Any catch?
There's the key nuance. It's a really important one. Yes, they break down, but how and where matters immensely. Often they need very specific conditions. We're talking industrial composting facilities, controlled temperature, moisture, microbes.
Not just my backyard compost heap.
Probably not. Without those specific industrial conditions, they might not break down completely. They could still persist and even form microplastics in the environment.
So biodegradable doesn't guarantee it disappears anywhere. What about examples?
Sure, some are petroleum-based, like PBS or PCL. Others are bio-based, like PLA. You've probably seen that in those clear compostable cups.
Okay, so even PLA, which comes from plants, might need special treatment.
Mm.
That leads us to bio-based plastics. What's the deal there?
Right. Bio-based means it's sourced, partly or maybe entirely, from renewable biomass, plants, basically. Corn, sugarcane, cellulose, things like that. The rule is generally at least 20% of its carbon has to come from biological sources.
Okay, comes from plants. Got it.
No.
Does that mean it breaks down easily?
And here's where it gets really interesting and potentially confusing. No. Being bio-based does not automatically mean it's biodegradable.
Really?
Absolutely. Take biopolyethylene or bio-PE. It's made from sugarcane ethanol, so it's bio-based.
Yep.
But chemically, it's identical to regular polyethylene made from fossil fuels.
Meaning it doesn't degrade any differently. It still lasts for ages.
Exactly. It retains all the non-degradable properties, so you've got bio-based plastics that are non-biodegradable, like bio-PE or bio-PET.
Okay.
Then you have bio-based plastics that are biodegradable, like PLA or PHA, and some can be designed to be both. So it's a spectrum. Bio-based only tells you the origin story, not the end-of-life story.
That distinction is huge. Definitely a source of confusion.
Yeah.
Okay, so where does compostable fit into this picture? Is that the ultimate disappearing act?
Compostable is essentially a subset of biodegradable. It's more specific. It means a plastic will undergo biological degradation in a composting environment specifically, an industrial one usually breaking down into water, CO2, inorganic compounds, and biomass. Crucially, it has to do this at a rate similar to other known compostable materials like paper or leaves. And it can't leave behind any visible, distinct, or toxic residues.
So it has to meet a certain standard.
Yes, there are certifications like ASTM D6400 in the US or EN 13432 in Europe. Seeing those certifications tells you it's designed for that specific industrial composting end of life.
Okay, that makes sense. Compostable means it's proven to break down cleanly under the right conditions. That clarity is vital. So now that we've got the definitions clearer, let's look closer at some of these specific bio-based plastics. You mentioned their overall carbon footprint is lower.
Generally, yes, compared to their conventional counterparts, and many can potentially be recycled multiple times, which is another advantage.
Let's start with the big one you mentioned, polylactic acid, PLA.
Right, PLA. It's currently the most produced bio-based polymer. We're talking over 140,000 tons a year, and producing it takes significantly less energy, maybe 25% to 55% less than traditional plastics.
And it comes from fermented biomass, like cornstarch. It's bio-based and biodegradable. Under the right conditions, we now know.
Correct. And it's really versatile. You see it in paper coatings, films, fibers, food packaging, even clothing. It makes a strong film, good barrier properties.
But you mentioned challenges.
Yeah, the main ones are that it degrades pretty slowly in like a normal natural environment, soil or water. And it can get brittle if exposed to UV light for too long.
And the recycling infrastructure isn't quite there yet.
It's still developing, so end-of-life management is key, especially making sure it gets to an industrial composting facility if that's what it's designed for.
Okay. What about polyhydroxyalkanoates, or PHAs? You said bacteria make these.
That's right, they're polyesters, synthesized by various bacteria. And the cool thing is, the bacteria can make them from all sorts of stuff, sugars, oils, even waste products like whey or captured CO2.
Wow, using waste to make plastic. That's pretty neat. What are they like?
They have really diverse properties. Some are quite crystalline and rigid, others are more elastic. They can be processed using standard methods like injection molding. You find them in packaging film, containers, bags, disposable things like nappies, cosmetic containers.
Any advantages over PLA?
One interesting one is they tend to block UV rays better than PLA does.
Okay, versatile, made from waste, potentially. Sounds promising. Let's switch gears to something maybe less known. Lignin-based plastics. What's lignin again?
Lignin is a complex polymer found in wood and other plants. It's actually a major byproduct of the pulp and paper industry. Huge amounts are produced, but it's often underutilized, sometimes just burned for energy.
But it could be made into plastic.
Yes, and it's surprisingly robust. Lignin-based plastics can have high mechanical properties, sometimes even stronger than polystyrene. We're talking tensile strength around 45 MPa versus maybe 35 MPa for polystyrene.
Stronger than polystyrene. That's impressive for a wood byproduct.
But here's where it gets almost futuristic. Lignin can exhibit shape memory properties.
Shape memory, like it remembers its original shape.
Exactly. And stimulus response properties. Imagine a medical stent made from lignin that changes shape slightly based on body temperature, or a coating that can self-heal minor scratches when exposed to humidity changes.
Self-healing plastic from wood waste. That's amazing.
It's really pushing the boundaries. Plus, it offers about a 30% lower carbon footprint compared to polystyrene production.
Are there downsides?
Yeah.
Limitations?
Well, lignin generally has a high glass transition temperature, meaning it needs more energy to melt and process. And sometimes plasticizers added to make it more flexible can migrate out over time, reducing its toughness. But the potential for these smart applications is huge.
Okay, mine's slightly blown by self-healing wood plastic. Let's cover the more familiar-sounding ones. BioPE and BioPET.
Right, biopolyethylene and biopolyethylene terephthalate. As we touched on, these are chemically identical to regular PC and peat made from fossil fuels.
But made from plants instead.
Exactly. BioP often comes from sugarcane ethanol. BioPET uses bio-based ethylene glycol, though usually still combined with petroleum-derived terephthalic acid.
So BioPET isn't fully bio-based yet.
Often not fully, no. The key thing about both is their compatibility. They can be drop-in replacements in existing manufacturing processes.
Ah, so industry doesn't need totally new machines.
Correct. They're scalable, compatible, durable, and highly recyclable through existing peat and PE recycling streams.
But the crucial trade-off.
They are not biodegradable. They behave exactly like conventional plastics at the end of their life. If they escape collection and recycling, they persist in the environment for centuries.
And costs.
Biopeat, for instance, is generally more expensive than conventional peat right now.
Okay, that's a super important point. Bio-based source doesn't mean biodegradable end. But for those plastics that are designed to biodegrade, what's actually happening at the molecular level? How do they break down?
It's a fascinating biological process, usually in stages. First is biofilm formation, or biodeterioration. Microorganisms need to colonize the plastic
They're
surface.
setting up shop.
Pretty much. They form a complex community, a biofilm. This can take time, days or weeks, sometimes called a lagging phase.
Okay, so they move in first, then what?
Stage 2 is hydrolytic depolymerization. The microbes secrete enzymes, specific proteins that act like molecular scissors. These enzymes break down the long polymer chains, the backbone of the plastic, into smaller fragments. Oligomers, dimers, and finally monomers, like snipping a long chain into smaller pieces.
Breaking it down piece by piece. And
Then comes mineralization or bioassimilation. These small molecules are small enough to be transported into the microbial cells. The microbes then use these molecules as food, essentially, for energy and growth through their metabolic processes.
and what's left?
The ultimate end products are typically carbon dioxide, if oxygen is present, water, and new microbial biomass. If there's no oxygen, like deep in a landfill, you might get methane instead of CO2.
So it becomes part of the natural carbon cycle again. What affects how fast this all happens?
Oh, many factors. The plastic itself matters, its chemical structure, purity, how crystalline it is, its molecular weight. Then there's the microbial community. Are the right kinds of microbes present? How active are they?
In the environment.
Absolutely critical. Temperature, pH levels, moisture, oxygen availability, even UV light exposure can all significantly speed up or slow down the process.
So a biodegradable label doesn't tell the whole story without knowing the conditions. What kinds of polymers are generally good at this?
Aliphatic polyesters are a key group. These have polymer chains that are relatively easy for microbial enzymes to attack. Think PLA, PCl, polycaprolactone, PGA, polyglycolic acid. They break down readily under the right conditions.
Okay, those are the more vulnerable ones.
Then you have materials like aromatic aliphatic copolyesters. A good example is PBA, polybutylene adipate terephthalate. These are clever hybrids. They try to combine the toughness and good mechanical properties you get from aromatic structures with the biodegradability of aliphatic segments. So you get a balance, strong, flexible, but still biodegradable.
A best of both worlds approach.
That's the goal, yeah. Then there are others like vinyl polymers. PVA, polyvinyl alcohol, is a well-known one. It's water-soluble, non-toxic, used in films, adhesives, even edible coatings sometimes.
And polyurethanes, PURs, aren't they usually quite tough?
They are incredibly versatile. You can design PURs to be biodegradable, often used for eco-friendly coatings or biomedical applications like scaffolds for tissue engineering. Some water-based versions are non-toxic and non-flammable too.
Sounds like a lot of potential. But you mentioned that caveat earlier, the risk of misinformation.
It's a really important point to stress. While these materials can biodegrade, many require those specific industrial composting conditions. If they're labeled biodegradable without clear instructions, or if the infrastructure isn't there, they might end up in landfills or the environment where they don't fully break down.
And could still contribute to microplastic pollution.
Exactly. So clear labeling and proper disposal infrastructure are absolutely essential for these materials to live up to their promise.
Which really brings us back to compostable plastics. They sound like the clearest case for a circular end of life, if handled correctly.
They really do represent that ideal, especially for certain applications. Composting itself is just nature's recycling process, breaking down organic matter into valuable compost or humus.
And compostable plastics are designed to fit right into that process.
Correct. They offer a great solution, particularly for plastics that get contaminated with food waste, making them hard to recycle conventionally. Think food packaging, coffee pods, cutlery.
You mentioned the Sydney Olympics example.
Yeah, back in 2000, they managed to divert a huge amount of waste, 76% of their solid waste, through composting, and that included compostable food serviceware. It showed it can be done at scale.
That's a powerful demonstration. And these compostable plastics, they can come from various sources too.
Yes, it's not just bio-based sources. Some petroleum-derived plastics like PBS, PCl, PEA, PVA can be designed to be compostable. And of course, many bio-based ones like PLA, PHA, TPS, thermoplastic starch, cellulose, even chitin or protein-based plastics can meet compostability standards.
It's about the performance in composting, not just the origin.
Exactly. And often manufacturers blend different biodegradable polymers. This can improve the physical properties, make it stronger or more flexible, and potentially reduce the cost. Like those Mater byproducts, often starch blended with other compostable polymers.
And where are we seeing these being used now?
Applications are quite broad. Packaging films, straws, shopping bags are common. But also in agriculture, compostable planting pots you plant directly, or mulch films that biodegrade into the soil.
Oh, interesting.
Even niche uses like fillers and tires are being explored. The aim is always, if it can't be easily reused or recycled, can it return to the earth safely and beneficially through composting?
Okay, shifting focus a bit now. Beyond the materials themselves, what about how they're made? Plastic production has traditionally been pretty polluting. Is that changing?
There's a huge push towards cleaner production methods. It has to happen. And we're seeing some really exciting innovations here. One standout is next generation industrial biotechnology, or NGIB, specifically for making PHAs.
NGIB. Okay, what makes it next generation?
It's a low-cost bioprocessing approach. It uses specially engineered bacteria extreme helimonas that can thrive in really harsh conditions, like high salt concentrations.
How is that useful?
Well, it means you can run the fermentation process using inexpensive non-food feedstocks. Things like treated kitchen waste, activated sludge from wastewater treatment.
Really? Using actual waste?
Yes, and even seawater can be used in the fermentation broth, which dramatically cuts down on freshwater consumption compared to traditional biotech.
That sounds like a huge advantage.
It is. NGIB also often eliminates the need for strict, energy-intensive sterilization because the conditions are too harsh for most contaminating microbes. It can be automated using AI for quality control. So you're looking at significant energy and water savings, lower equipment costs, making these bio-based PHAs much more cost competitive.
That really could be a game changer for scaling up PHA production. What other clever production ideas are out there, turning waste into value?
Absolutely. Another really interesting area is making bioplastics from inedible fruit parts. Waste valorization, basically.
Okay, like what kind of fruit parts?
Well, take coconut shells. They're abundant in many regions. Researchers are turning them into biocomposites. These materials can have impressive mechanical strength and thermal stability, so you get a sustainable material that might even last longer in some applications. Treating the coconut fiber with alkali can improve properties and energy efficiency, too.
Coconut shells.
Okay.
What else?
How about orange peels? Huge amounts are generated as waste from juice production.
Makes sense. Lots of peels left over.
They're rich in cellulose. And researchers have found ways to convert them into bioplastics using fairly simple methods, mechanical crushing, chemical mixing. It uses way less energy than making conventional plastics.
Simple process, less energy, uses waste.
Mm-hmm.
Sounds ideal. Do they break down well?
Early tests are promising. In one study, orange peel bioplastic buried in soil showed about 33% degradation in just 31 days.
33% in a month, compared to centuries for regular plastic.
Exactly. It significantly reduces that long-term pollution risk.
So where is research heading in this cleaner production space? What's next?
A lot of focus is on improving efficiency, getting higher yields of bioplastic from the feedstock, better control over the material properties like molecular weight, developing new copolymers by blending different bioplastics to get specific characteristics, and exploring green solvents, safer, more environmentally friendly chemicals to use in the production processes. It's about making the entire life cycle cleaner.
Okay, so we've covered definitions, types, production. Let's get practical. With all these options, what's actually feasible now for widespread use, and what's still more on the horizon?
Right, the reality check. If you're looking at the mass market, especially for items intended to be reusable or easily recycled, then BioPP polypropylene and BioPE are strong contenders.
Because they fit into existing systems.
Exactly. They're scalable, manufacturers are familiar with them, they're durable, and crucially, they can go into the established recycling streams for PPP and PE.
But we have to keep repeating the caveat.
They are generally not biodegradable. Recycling is absolutely key for these.
Okay. What about things designed for single use, where biodegradability or compostability is the goal?
There, BioPLA and BioPBS polybutylene succinate are good current options. PBS, especially when blended with other materials, shows a lot of promise for flexible packaging applications.
And those high-end PHAs.
For high-performance biodegradable applications, BioPHA and related BioPHB polyhydroxybutyrate are very effective materials. But, as mentioned, their higher cost is still a limiting factor for really widespread use right now.
So cost is still a barrier for some of the most advanced options. Now, this journey has been fascinating, especially exploring these newer materials. Are there other, maybe even more out there substitutes emerging? Things that go beyond what we usually think of as bioplastics.
Oh, absolutely. This is where the material science gets incredibly exciting. We're pushing beyond just mimicking traditional plastics.
Okay, give us some examples.
One is cellulose nanofiber, or CNF. This is derived from plant cellulose, the most abundant polymer on Earth. But when you process it down to the nanoscale, CNF becomes this incredibly strong, stiff, biodegradable structural material.
Oh, strong.
Get this. Its mechanical and thermal properties can actually surpass many traditional petroleum-based plastics. We're talking flexural strength around 300 megapascals, modulus around 16 gigapascals.
Wow. That sounds like serious engineering material territory.
It is high performance, but it comes from plants and it's biodegradable. Game-changing potential.
Okay, stronger than plastic, from plants.
Yeah.
Biodegradable, mined, slightly bone. What else is super innovative?
How about hybrid minerals, or HM? These are flexible, degradable materials made from calcium phosphate oligomers. It kind of mimics how nature forms minerals in living organisms, biomineralization.
Hybrid minerals. What are they like?
They offer really good hardness and stability at high temperatures, better than many polymers. They can be molded easily. And here's a fascinating idea. The researchers suggest that because it's mineral-based, it could potentially participate in geological cycles after disposal. It might just become part of the rock cycle again.
A plastic substitute that rejoins the Earth's geology. That's a radical concept.
It really is. Then you have mycelium-bound materials.
Mycelium.
Yeah.
That's mushroom roots.
Exactly, the root structure of fungi. You can grow mycelium around agricultural waste like sawdust or straw, and it binds it together into a solid material.
What's it good for?
It's biocompatible, fully biodegradable, often quite flexible, naturally fire-resistant, and some researchers are even exploring self-healing properties.
Self-healing mushroom packaging.
Or textiles, building materials, automotive parts. Plus, they can have antibacterial and antioxidant properties. Really versatile stuff grown from fungi.
Okay, mushrooms joining the material revolution.
Yeah.
Incredible. Anything else pushing the strength boundaries?
Yes. Think spider silk-inspired materials. Not actual spider silk, which is hard to farm, but materials designed to mimic its incredible properties, often using proteins like soy protein isolate.
And are they as strong?
They can achieve exceptional strength and toughness, sometimes outperforming both other bio-based plastics and even some traditional ones. They also show remarkable water resistance, staying strong even after being soaked. And production can significantly cut down on volatile organic compound VOC emissions compared to making conventional plastic films.
Plus, they're degradable.
Naturally degradable, thermally stable, and potentially recyclable, too. A really compelling combination of performance and sustainability.
Amazing. One more.
Let's mention wood powder material, or WPM. This involves binding wood powder, essentially sawdust, together, often with a biodegradable binder or through compression techniques. It creates a sustainable material that actually captures CO2 as the trees grew. Its strength can be comparable to plastics like ABS.
And production. Disposal.
Production is generally less energy intensive than making virgin plastic. And upon disposal, ideally through composting or even incineration under controlled conditions, it primarily generates just CO2 and water. It's an elegant use of a widely available natural resource.
Wow. Okay, so we've really covered a lot of ground, from the sheer scale of the plastic problem and its hidden costs.
To really unpacking those confusing terms, bio-based, biodegradable, compostable, and why the distinctions matter so much.
We looked at specific types, the good and the bad, the innovations in making them cleaner.
And then these truly mind-bending emerging materials, from nanocellulose and minerals to mushrooms and spider silk mimics, it's clear innovation is moving fast.
Absolutely. And if
Yeah.
there's one big takeaway, it's probably that there's no single magic bullet, right?
Definitely not. Solving the plastic problem needs a multi-pronged approach.
Mm.
Better recycling, definitely. Clearer definitions and honest labeling, supporting these innovative new materials.
And conscious choices from all of us.
Absolutely. Consumer demand and understanding play a huge role.
And hopefully, this deep dive helps with that understanding. Knowing these distinctions empowers you, our listener, to ask better questions, make more informed decisions about what you buy, how you dispose of it. It all helps shape a more sustainable path forward.
So let's leave our listeners with a thought. Considering the incredible properties we just discussed, cellulose nanofibers stronger than plastic, self-healing mycelium, spider silk films, what existing industries could be completely turned upside down by these next-generation alternatives?
And thinking beyond that, what unforeseen impacts, good or bad, might that revolution have on how we use resources globally? Something to ponder.